In this video, I want to look at how we go about drawing a straight line graph from a set of data that is given and how we can find the gradient of a straight line. I will first go through the points to bear in mind when drawing a graph and then work through an example, following which you'll get the chance to work through two other questions on your own, and then we'll look at the solution at the end. So first of all, why do we use graphs? A graph can be used to show how one quantity relates to another. So for example, if an experiment is conducted to investigate the relationship between two quantities, generally what would happen is that you take measurements of both quantities while you vary one and see how the other one responds. And then a graph can be used to analyze the relationship between the two quantities because it gives you a picture of how one quantity changes when the other is varied. A graph can be a way of averaging a set of results as well, rather than trying to calculate a quantity based on just two values. We can do a graph that shows many values, and from that graph, we can get an average of the results that is likely to be more accurate than just one set of readings. We can also use a graph to predict what the value of a quantity would be outside of the range of values that we have, but just based on the trend or the pattern that we observe from the graph. So first I want to look at points to note when drawing a line graph. And for the most part, in physics, we work with line graphs. Not always a straight line, maybe a curved line, but a line nonetheless. So your graph should always have a title, and that title must indicate what are the quantities that you're plotting on the graph. Each axis should be labeled with the quantity and the unit. And as a rule, the labeling of the axes must correspond to the title. So whichever quantity is named first in the title goes on the y-axis. Whichever quantity is named second in the title goes on the x-axis. So generally it's y against x. If you're plotting a graph of length against time, if that's what the title says, then length goes on the y-axis, time goes on the x-axis. So the labeling of the axes must correspond to the title, and also each axis must be labeled with both the quantity and the unit that that quantity is measured in. The scales that you use on the graph axes should be such that the graph should occupy more than half the grid area. So you want to make sure that when you have plot the points and drawn the graph, the area that you're taking up is more than half the available area in both directions. The scale should also be simple, easy to use, and suitable, meaning that each line on the scale should represent a definite number. The points are marked using either an X or a tiny dot with a circle. So the dot, if you're using the dot with the circle, the dot should be really small so that the circle is just there to help you identify where the dot is. It shouldn't be a big blob, just a tiny dot with a circle around it. Or if you prefer, you use the X, and right where the two lines that form the X meet, that's exactly where the point you're plotting is. To draw the line of the graph, you should consider whether the origin is a point on the line, and that depends on the context. So we will look at that in our examples as well. And the line should be drawn using a sharp pencil, and it should be a line of best fit. Whether it's a straight line of best fit or a curved line of best fit, it should be a line of best fit, meaning a line that fits the points as best as possible. And that we will also illustrate through the example. These are the steps in finding the gradient of a straight line. And we will go through this as we work through the example. So here's the first example. A measuring cylinder is part full of water. It is placed under a dripping top and readings are taken as follows. So we have readings of time in seconds and volume in milliliters. So over a period of 600 seconds, we see that the volume was measured at 100-second intervals. So at the start, there was already 104 milliliters in the measuring cylinder at time 0. And these are the readings of volume at the various times. First, we're going to plot a graph showing volume against time. Right away, we know what our title should look like, because these are the quantities that we're going to be plotting, volume against time. Probably the simplest way you could write the title is to write volume versus time. Versus here meaning against. If you want to write a more elaborate title, it's up to you. But the important thing is both quantities must be named in the title. If you write a title that says graph showing results of an experiment carried out in a lab, that title is not saying anything about the quantities that were measured, so that's not an appropriate title. Your title must name the quantities that you're going to plot. So for the labeling of the axes, we can see from the table here that there are no negative values, so we can put our axes at the extreme left and the bottom of the page, using up as much of the space as possible. The labeling of the axes with quantity and unit. If the title says volume against time, volume must go on the y-axis, time must go on the x-axis. If it said time against volume, then time would go on the y and volume on the x. Okay, so the quantity that is named first goes on the y-axis, the quantity that is named second goes on the x-axis. And each axis must be labeled with both the quantity and unit. And this is how we do it. Quantity slash unit, or as it is in the title, you could also label the axis quantity with the unit in the bracket beside it. That also works. Our next step is to choose a scale. And remember, we said the scale must be suitable and it should occupy more than half the grid area. So on the time axis, we have values from 0 to 600. And we want to spread that out so that it takes up as much of the page as possible. Now, if we count how many centimeters squares we have here, there are 18. So one might say, okay, let's divide that into 3-centimeter intervals. So we have 3 centimeters representing 100 seconds. But wait a minute. That would allow us to use up all the page. But wait a minute. The scale may not be suitable for another reason. Let's check how many seconds are represented by 1 centimeter. If we have 3 centimeters representing 100 seconds, then 1 centimeter will represent 100 divided by 3, which is 33.33 3, 3, 3, 3, and the threes go on and on. They're recurring. So this is a recurring decimal. That makes this scale unsuitable. Each line on the scale must represent a definite value. We cannot have a line on the scale representing something that is a recurring decimal. So that is an unsuitable scale. The line can represent a decimal. It doesn't have to be a whole number. It can represent a decimal, but it must not be a recurring decimal. So that is what makes this scale unsuitable, because you're saying 1 centimeter represents a value that is not definite. So let's try another scale. If we use 2 centimeters to represent 100 seconds, that means 1 centimeter will represent 100 divided by 2, which is 50 seconds. That's okay. That can work because it is definite, and it can also work because even though we're not taking up the entire width of the page anymore, we're still using up more than half the page. Okay? So that scale is appropriate, it's definite, and it occupies more than half the page. Okay. Another point to note, the scale on the y-axis does not have to be the same as the scale on the x-axis. Consider them separately. They're independent of each other. So we go about choosing our scale for the y-axis considering the same rules. We want to take up more than half the page, and we want it to be such that each line represents a definite value. Now, something else to consider. The values that we're using here for volume, the lowest value is 104, the highest value is 140. So it is not necessary for us to start the y-axis scale here at 0, because if we start at 0, our first point is going to be 104. We would definitely not be using up as much as half the page if our page even goes from 0 to 140. The first 100 units will not be used, will not be needed. So our graph would only be occupying maybe a fraction, less than half, would definitely be occupying much less than half the page. So we want to choose a scale that will spread out the range of values that we have to plot over more than half the page. A common mistake that some students make is to simply take the values from the table and just space them out along here with no regard for scaling. You can't just put 104 here, 110, 117. That would not be a scale. A scale should have equal distances representing equal values of the quantity. Okay? For the time axis, it might look like that's what we did. We just took the values from the table and spaced them out along this axis. That's not exactly what we did. It so happens that the values in the table are equal intervals apart, so they match the equal spaces that we have here. The values for volume don't vary like that. Okay? They are not equal intervals apart. So what we do is to look at the range of values. Let's say we start at 100 and go up to 140, just for easier scaling, just for convenience. We'll start at 100. So 100 goes where the two axes meet. You do not have to start the scale at 0. You also don't have to start at 0 and break the axis. You can start at 100. You can start at a convenient value depending on the values that you have to plot. So we will start at 100, and we want to spread out our values so that we can get to 140 in equal intervals. So in choosing the scale, Don't focus on the in-between values that you will have to plot. We will look at those later. We're just looking at the range of values, 100 to 140. And we want to spread that out along this axis so that it takes up more than half the page. So we could probably use 4 centimeters to represent 10 milliliters. Let's see. 4 centimeters, this would be 110, 120, 130, 140. That will work. Depending on the size of your page, you could probably work with something larger. But I'm working with 2 centimeters for 5 milliliters. Okay. Now let me just zero in on that a bit. 2 centimeters to 5 milliliters. That means if we're taking the 5 milliliters and dividing it into 10 parts, each tiny block on our scale here will represent half a milliliter. 5 divided into 10 parts. So 2 blocks will represent 1 milliliter. Okay, we need to bear that in mind when we're plotting the points. So you always need to work out at the start how much of the quantity does one of your smallest divisions represent. In this case, on our volume axis, 2 of the smallest divisions, 2 of those 2 millimeter squares represent 1 milliliter. So if this is 100, 101, 102, 103, 104, 105. On our time axis, it's a different scale. Here we have 100 seconds divided into 10 parts. So each division, each of the smallest divisions on this time axis is representing 10 seconds. So now we have our scales. We're going to plot the points. First point, at time 0, the volume is 104 milliliters. So at time 0, we're going to 104 milliliters. That's where our point is. Don't go to 105 and say, okay, 105 minus 1 gives us 104. Remember, one of the divisions on our scale does not represent 1 milliliter. It only represents half a milliliter. So we need 2 of our smallest divisions to give us 1 milliliter. 100 seconds, we have a volume of 110 milliliters. 100, 110. 200 seconds meets up with 117 milliliters. Again, that's 4 divisions up from 115. 115, 116, 117. And we continue to plot the points. 121 to 300. 400 goes to 129. 500 goes to 133. Remember, it's 2 divisions to 1. So 131, 132, 133. And 600 goes to 140. So once we have plotted the points, time to draw our line of best fit. Obviously, all the points won't fall exactly on a straight line, but we are going to draw a straight line. Never you join the dots. We want one straight line. All the points may not necessarily fall on the line, but we want the line to be as close to as many points as possible, and we want balance. So the points that do not fall on the line that you have drawn should be evenly distributed as far as possible. So let's see, if you draw the line looking like this, we have 2 points on the line. This point is slightly off on that side. On the other side, we have 4 points that are not on our line. This line is not a best fit line because the 4 points on this side, there are too many points on this side compared to what's on the other side. And these points are much further away from the line than the one on the other side. So there is no balance here. So this is not a line of best fit. When you draw your line of best fit, do it with a sharp pencil, do it lightly so that in case you don't get it right the first time and you have to erase it, it will not be messy. So this is a better line of best fit. It doesn't have as many points on the line. In fact, there are times when you could draw a line of best fit and none of the points that you marked are actually on the line. But the line passes through the middle of the points and they're all as close to the line as possible. So we have 2 points here that are on the line. We have 2 on this side, 3, this one is slightly off. And on the other side of the line, we have 2. So there is some balance here, okay? If it's an odd number of points that are not on the line, then no more than 1 extra on either side. If it's an even number of points, they should be evenly distributed. Okay, so this is the graph. That's part A of the question. Part B says find the rate at which the water is dripping by finding the gradient of the graph. So let's talk about gradient. Gradient simply means the slope of the line or the steepness of the line. It tells you how many units of increase you have on the y-axis for every 1 unit of increase on the x-axis. So it's really the rate at which the y-axis value is changing in relation to the x-axis value. So the higher the gradient, the steeper the line. How do we find gradient? First step is to choose any 2 points on the line that you have drawn. So that line of best fit that we drew, we will choose 2 points on the line, and those 2 points do not need to be any of the points that you marked previously. We marked some points with an X, or maybe used a dot with a circle. But once you have drawn the line, forget about those points that you actually marked. A line is a set of points. So anywhere along the line you drew, you can find a point to use for finding the gradient. The other thing to consider is that the distance between the 2 points should be at least half the length of the line of best fit. So this is our line of best fit. What I am saying is, in choosing the 2 points on the line, forget about the ones that you marked with an X. Never you just go to the table and say, okay, let's just choose 2 points from the table and write down the coordinates of those points. No, because you may select a point from the table that didn't even fall on your line of best fit. You can't be finding the gradient of a line using a point that is not on the line. A line is a set of points. So anywhere along this line, we can choose a point. Choose a point conveniently. Meaning, you'll need to write down the coordinates of the points that you choose. So choose a point where your best fit line that you drew coincides with the intersection of 2 of the grid lines so that you can easily read off the coordinates. So for example, if I choose a point here, this was not an original point from the table, and I can also choose a point up here. far away from the first point so that the distance between the 2 points that I've chosen is more than half the length of the line. And the point is also convenient here because it's at the intersection of two of the grid lines with my best fit line. You can't just choose a point somewhere out here. Say, okay, two lines intersect, let me choose this point. No, the first thing, it must be a point on your line that you drew. And remember, it doesn't have to be a point that you marked with an X. Anywhere along the line, because a line is a set of points. Once we have chosen the points, we're going to write down the coordinates. You should use a broken line to form what we call the gradient triangle. So it's a triangle where the 2 points that you're using to find the gradient are at the ends of the hypotenuse of your triangle, and it's a right angle triangle. This should be a big triangle, okay? So when you look at the graph, when your teacher looks at the graph, immediately he or she can see which 2 points you use to find the gradient and can see that they're far enough apart because you have a big gradient triangle. Write down the coordinates of the points. Okay. Okay, we need to add to our scale here so that we can read off the coordinates of the points. So we're going up to 700 and up to 145. So we're writing down the coordinates of the points that we're going to use to find the gradient. This is point number 1. X coordinate is 50. The Y coordinate is 107. We write X coordinate before Y coordinate. So it's X1, Y1. The ones just mean that this is the first point that I'm using. Similarly, for the second point of here, X2, Y2. The X coordinate for this point, come down here, read it off, 650. The Y coordinate, we come across here and we read it off, 142.5. It's halfway between 140 and 145. Make that a little bigger. 140, 141, 142, 142 and a half. So we write exactly what we read off. We don't round off and try to avoid the decimals. We read off exactly what the scale says. So the coordinates for the second point, x2 is 650, y2 is 142.5. Those are the values now that we're going to use to find the gradient of the line. So the formula for the gradient, y2 minus y1 divided by x2 minus x1. So substituting the values, it's 142.5, that's the y2, minus 107, that was the y1, divided by 650 minus 50, x2 minus x1. So what you're really finding is this distance over this distance. The height of your gradient triangle divided by the base of your gradient triangle. That's what your gradient is. So when you do that calculation, depending on how you draw your best fit line, you should get approximately 0.059 or 0.06. Everybody may not get exactly the same value because it depends on your best fit line, but it should be close if your line is the best fit for this graph. Your gradient must also have a unit. You're dividing the change in the quantity on the y-axis by the change in the quantity on the x-axis. Your gradient must have a unit that reflects that. So the unit for the gradient is the unit from the y-axis divided by the unit from the x-axis. So the gradient here is 0.059 milliliters per second. and that is the rate at which the water is dripping, because it is telling you that for every 1 second change in time, the volume changed by 0.059 milliliters. So it's telling you the rate at which the water is dripping. Okay. For part C, we're now going to use this graph to answer the question, after how many seconds was the volume 125 milliliters? So, since the graph already shows us the relationship between the volume and the time, we're going to just look at the volume of 125 milliliters and see where that meets our line of best fit and read from that the time. So at 125 milliliters, that corresponds to 350 seconds, reading from our scale here. So the answer for C is 350 seconds. And then for D, what was the volume after 150 seconds? On our time scale, we're looking for 150 seconds. Follow that line until you get to where your line of best fit is and read from this scale the value of the volume. So remember that on this scale, 2 of our smallest divisions represent 1. So if the line is here, it means we're at 113 milliliters. Because coming down from 115, 114, 113. Or if you're counting up from 110, 111, 112, 113. So the answer for D is 113 milliliters. Let's just quickly look at some terms that we sometimes use in relation to graphs. To interpolate means to find an intermediate value within the range of known values. So that's actually what we did for parts C and D of the question. We interpolated. We found intermediate values of the quantity that were not actually measured. We measured for 121 and we measured for 129, but to find the in-between value of 125, we had to interpolate. Extrapolate means that we're finding a value outside of the range of known values by assuming the same trend continues. That's what we did, and we had to find the coordinates for this point because our range of values stopped at 140, but we had extended the line assuming that the same trend would continue, so we could now find a value outside of the range that we knew. Beyond 600 seconds, we could find a value of volume for 650 seconds by extrapolating. The y-intercept of your graph is the value of y when x equals 0, and our x-intercept is the value of x when y equals 0. So for our graph that we drew, we had no x-intercept because volume equals 0 was not included in our range of values. So there's no x-intercept on this graph, but there is a y-intercept. That was the value of volume when time was 0. That was our starting point. Okay. So this is another example. You can pause the video right here and try this one on your own before you look at this solution. So your graph should look something like this, with your title saying mass against volume, mass on the y-axis, volume on the x-axis, with suitable scales, taking up more than half the page in both directions, Plotting your points and then drawing your line of best fit. In this case, though 0, 0 was not a point in the table, based on the context, we know that the line should pass through 0, 0 because the situation was that you had the mass of the pins, and for each mass, you had the volume that was measured. How we know that it's supposed to pass through 0, 0? Because if the mass was 0, that would mean you had no pins, and no pins would take up no space. So if the mass is 0, the volume would be 0. Or if the volume is 0, if the pins are not taking up any space, then it means there are no pins, because if it has mass, it must have volume. So there is no x-intercept or y-intercept for this graph. It must pass through 0, 0 because you can't have mass without volume or volume without mass. So both quantities must be 0 at the same time. Hence, we draw the line starting from the origin. Gradient of the graph, choose your points. In this case, I chose 1 point here, and I chose to use the origin, the 0, 0, because I'm sure that the line must pass through 0, 0. So I chose the origin as one of the points to use to find the gradient. The other point is here with coordinates 3 and 23 based on the scale that I'm using here. And so my gradient is 7.7. And the unit for the gradient, again, the unit on the y-axis, that's grams, divided by the unit on this axis, which is cm cubed. So the gradient is 7.7 grams per cm cubed. Now the next question asks, what quantity does the gradient of the graph represent? This would require some prior knowledge. The gradient is telling you how much mass there is for every unit of volume. And by definition, that's what density is. So density is the answer for part 3 because density is mass per unit volume. So that's how you would find the density of the pins using the graph, just by finding the gradient. And then we are asked to calculate the volume of 50 grams of the pins. Now the range of values we have on our graph stops at 25, so we can't read that from the graph, but we can use our knowledge of density. Density is mass over volume. So volume is mass divided by density. So for a mass of 50 grams, we can divide that by the density that we calculated from the gradient of the graph. And so we get a volume of 50 divided by 7.7, which is 6.5 cm cubed. Notice the unit again must match the unit that we were using here. We're saying 50 grams divided by 7.7 grams per cm cubed will give us 6.5 cm cubed. And there is one more example that you can try. Again, you can pause and work on this one before looking at the solution. A girl walks one lap around a 400-meter track. For the first 300 meters, she records her distance from the finish line at 50-meter intervals and the time for which she has been walking. So she started 400 meters from the finish line at time 0, and every 50 meters she recorded the time. So 350 meters from the finish line, that was after 1 minute. 300 meters from the finish line was after 2.2 minutes, etc. All the way down to 100 meters from the finish line, that was after 6.3 minutes. You're asked to plot a graph of her distance from the finish line against time, and use the graph to find the time when she gets to the finish line, assuming she continues to walk at the same rate. we also want to find the gradient of the graph. You can check that your graph meets all the requirements: title, scale, axes labeled, points marked correctly, whether with an X or the dot with the circle, your line of best fit. So this graph has a line that slopes in such a way that we know it has a negative gradient because the distance is decreasing over time. Remember, this distance is being measured from the finish line. So she started 400 meters from the finish line, and as she walked closer to it, her distance from the finish line was decreasing, hence the negative slope of the graph. Part B says use your graph to find the time when she gets to the finish line, assuming she continues to walk at the same rate. So the graph, the values from the table stop at 100 meters from the finish line. If she's walking at the same rate, then we're assuming that it's the same trend. So we can extrapolate, extend this line until we get to zero distance from the finish line. That would mean she's at the finish line. So when we extend the line, we see that it crosses the x-axis, the time axis here at 8.4 minutes based on the scale we're using. So that's the answer for part B. We simply extrapolated, extended the line until we cross the time axis, and that gives us the time when she gets to the finish line, the time when her distance from the finish line is zero. And we're also asked to calculate the gradient of the graph. Same procedure. Choose 2 points on the line. This is one of my points, and this is the other, far enough apart. And we're putting in our gradient triangle and writing down the coordinates. So here, according to the scale we have, the x-coordinate for the first point is 0.5, and the y-coordinate is 375. On this y-axis, we have 50 meters divided into 10 parts. Smallest division represents 5 meters. So this line represents 375. That's our y1 coordinate. Next point, x coordinate is 7 and the y coordinate is again, remember each division represents 5, so this is 55, 60, 65. 65 for the y coordinates. So if we are to put those into our gradient formula again, y2, that is 65, minus y1, which is 375. Yes, if we're starting with this point, then the y2 is a 65, the y1 is a 375. Never mind the fact that the 375 is bigger. We must stick to the rule. It's y2 minus y1. And x2, which is 7, minus 0.5, which is the x1. If we started with this as our x2 and y2 and said 375 minus 65, then our denominator would be 0.5 minus 7. We would still end up with a negative value for our answer. So it really doesn't matter which point you call point number 1 and which point is point number 2, but once you have labeled them as such, you can switch the coordinates because you don't like negative numbers. You must substitute exactly as they are written. So the gradient for this graph is negative 310 divided by 6.5, which gives us negative 47.7 and the unit is meters per minute. We could probably round that off to negative 48 meters per minute at this point. That is telling you that every minute her distance from the finish line decreases by 47.7 meters, hence the negative value. Hopefully, this has given you a firm enough foundation to build on as it relates to graph work in physics.